My name's Andy Nisbet. I'm a research fellow at Manchester University, and we're trying to create tools centered around eBPF, that's the extended Berkeley packet filter, which provides a dtrace-like tracing technology. We want our tools that we're trying to create, we want to enable fair comparisons of the execution performance of applications, irrespective of what language they're written in. In the context of GraalVM, we want to use this to evaluate the performance issues in truffle language implementations. So we need to use the full stack to identify where time is spent. What do we mean by that? We mean not only the application and VM code, but also any libraries and the OS. Further, we want to identify why the underlying processor microarchitecture might not be effectively utilized. To do this, we need to use performance counter metrics to identify the likely causes of inefficiency. And we really want to be able to understand dynamic per thread behavior. Okay. So what is the process of performance analysis abstractly that we want to perform? It involves identifying the data sources that are to be measured by sampling or instrumentation, the observations that are logged during execution. Ideally, they should introduce as little overhead and interference as possible. And we then need to analyze and process our observations to generate metrics and visualizations that can aid the detection of performance issues. There are many different visualizations that could be used. In this talk, we will briefly cover flame graphs. We're not advocating flame graphs for everything, but we're just saying that's what we're going to cover in the talk. So the main outline of what we're going to cover, we're going to discuss flame graph visualizations and summarize the shortcomings between JVM and OS-based techniques for constructing them. We will briefly discuss an approach to resolving truffle guest language method names in flame graphs. We will introduce the concepts behind full stack tracing and highlight how it could be useful to de-optimization. We will also discuss how top-down analysis can be used to aid performance bottleneck analysis in order to identify how well or how badly a process or microarchitecture is being utilized. And we will present ideas behind our work in progress tool, BCC Java, for full stack analysis. And finally, we'll conclude with conclusions, a discussion, and acknowledgements of funding. So, a simplified flame graph. Here's some simple pseudo C code. It's a very simple example. It performs some initialization, then it performs computation, and finally it performs some output. 20% of the time is spent in initialization, 60% of the time is spent in computation, and 20% of the time in output. So how can we use Callstack sampling to indicate where time is spent? We have a timeline in this slide that indicates which method is executing on the CPU core at any instant. Sampling profilers repeatedly collect snapshots of call stacks that are a list of code addresses that can be resolved to function names. Call stacks describe the on-core execution context of threads running on a core at the sampled moments in time. You could imagine taking a call stack is like typing where in GDB when a program is at a breakpoint. The total execution time of specific methods is statistically related to the number of times a method appears in all stack traces. Now, this is only true as long as the samples are collected fairly and that all points in a program execution are selected randomly to remain statistically independent. High stack sample numbers indicate where time is spent. More time is spent in evaluate, so it has more stack samples. Now the question is, how can we visualize this in order to easily see where time is spent? Now it's possible to create a visualization known as a flame graph, where we create a scalable vector graphic that can be viewed in a web browser. Here, the call stack column width is proportional to samples, that is in turn statistically related to time. Columns are alphabetically ordered in the flame graph. They are not, or they can be ordered by width, but they are not an execution time schedule. They allow us to characterize the execution, not just what is happening in the application, but also even extending to the OS. So in this example, we can see that 60% of the time, 60% of the column width is given over to the evaluate call stack, and that happens to correspond to 60% of the time. So let's look at a real example collected using the OS perf mechanism. So here's an example to give you a feel for what can be seen using perf OS-based call stack sampling. Code addresses in call stacks can be mapped to different types of code regions. Therefore, it's possible to identify C++, JIT-compiled Java, and the kernel, the OS kernel, and to color them appropriately. It's even possible to identify inline jittered code, colored aqua. But it's not all good news for perf-based call stack sampling, as it needs help to be able to map jittered code addresses to method names. This information needs to be extracted from the JVM. Also, we only see interpreter in the call stack columns. We cannot see which method was being interpreted. On a more positive note, flame graphs can be searched in the browser, and the total contribution of a method is seen and highlighted across multiple call stack columns. We can see that GC thread activity was significant for this benchmark. A key question is, when are call stacks sampled? Well, they can be sampled using programmed overflow of a counter for CPU cycles, or a performance counter even, or we can use software callbacks or instrumentation code can decide using software tracing to take a call stack. It's important to note that frequent sampling and tracing increases overhead. And you must be wary, the width is proportional to the overall stack samples. In a multi-threaded environment, this is not the same as wall clock time. This slide summarizes the main findings from our ICP-19 paper. Bold highlighting indicates bad things. So a general point with CPU flame graphs is that it represents an average where time is spent in execution. A frequently short but intimately long duration operation will appear as a narrow column width, meaning that important performance issues can be obscured or hidden and not appear significant. Remember, perf doesn't see the identity of interpreted methods, and perf needs a mapping between JIT code addresses and method names. JVM get call trace samplers suffer from safe point bias. This means potentially they can lead to identification of the wrong methods as being the hottest or most time consuming. JVM samplers in general suffer from incomplete code coverage. They cannot see all JVM intrinsics or stubs. For example, things like system.arrayCopy. Hybrid profilers use perf and get async call trace, by doing so, they can avoid sampling bias, but they still suffer from incomplete code coverage within the JVM. So, where are we up to in the talk? We're now going to talk to you about truffle-based language performance and how to visualize guest language methods. Sulong is a truffle guest language that enables a program that is being compiled to LLVM-IR to be executed on GraalVM. Sulong guest language methods are represented as instances of truffle call target methods. The question is, how does Sulong performance compare to other truffle languages? Well, the Shootout benchmarks provide an opportunity to attempt to fairly compare the performance of benchmarks written in different languages. This graph is taken from our Manlang 18 paper. It demonstrates significant performance variation between native C, Sulong, Truffle Ruby, and FastR. The performance in this graph is normalized to that of Java. It's important to note as well, this is warmed up performance in this particular graph. But what we want to be able to do is answer the question, is why is Truffle language A faster than Truffle language B on a specific benchmark? To do this, the first thing we tried to do was to look at a flame graph collected with perf call stack sampling. We want to try to identify where time was spent, or at least to identify the significant methods. Unfortunately, we only see the truffle call root methods. We do not see the guest language source code methods. Call root obviously indicates this is a guest language method, but we do not know which one. Different call root methods have different code addresses, so we need to extract information relating call roots to guest methods. This requires additional information from JIT compilation. In order to make the n-body LLVM-IR guest language method visible, we added some extra logging to GraalJIT compilation to be able to map truffle call root addresses to the guest language methods. I haven't experimented much with VisualVM or GraalVM's CPU sampling profiler, but I believe that similar work has been done there too. Note, as this is a perf-based flame graph, we can still see the full stack, the OS, and the library code. Where are we up to in the talk? We're now going to talk to you about full stack tracing instrumentation using eBPF, which is another OS-based mechanism. What is full stack tracing? If you remember, by full stack, we mean all the code that is executing, the JVM libraries, the application, any truffle code, and the OS, absolutely everything. So far, we have only looked at sampling. We have not counted or measured anything directly. We briefly mentioned earlier that important performance issues due to intermittent, long or slow operations can be obscured in a flame graph, only appearing as narrow columns. And surely, if we choose to measure rather than sample, then we will be able to see the intermittent, long or slow operations, or to see their execution. Tracing is focused on measuring rather than sampling information from data sources. So we will now attempt to describe how we can use tracing to identify and understand performance issues. So, towards full stack tracing instrumentation, here is the full stack for a GraalVM application. We've highlighted the trace points where we can efficiently attach instrumentation using eBPF. And remember, eBPF is just an instrumentation mechanism that is largely equivalent to dtrace. eBPF, it works on Android and Linux and is available on ARM and x86 processors. It is important to note that the full stack extends to include measurement of performance counters. We need these counters to understand the behavior of processor microarchitecture instrumentation, or processor microarchitecture. Instrumentation means we can accurately measure rather than sample. Plus, we can selectively capture information at points of interest. For example, if a thread blocks for longer than a program duration, then we could capture the blocking and the waking thread's call stack to develop insight into the causes of long blocking operations. This enables us to go beyond studying overhead only due to CPU utilization. It's important to note that when one adds instrumentation with eBPF, you can either use, you can typically use a trace point that makes it very efficient to do so, and you can also use probes where you can instrument any known address or text symbol. So, for example, it's important to note that the GraalVM libjvm.so methods and symbols can therefore be instrumented if their debug symbols are known. So, let's look at our use case. How can we apply tracing to investigate de-optimization? What do we need to measure? Which de-optimization related method in GraalVM's libjvm.so do we need to investigate? Now, obviously, GraalVM, one of its strengths is it aggressively applies speculative optimization to yield better optimized code. Unfortunately, this will incur de-optimization when assumptions are found to be false, such as on class loading a new definition of a method X that has already been compiled. De-optimization means that the stack must be transformed from optimized layout, potentially leading to code cache invalidations and also to the execution of slower and even interpreted versions of code compilation units. A key question is, how can we identify which de-optimizations to focus on? The ones that happen a lot, the ones that take a lot of time, or the ones that lead to much slower code to be executed? Can we identify what caused the de-optimization by taking a call stack of Graal de-optimization method in libjvm.so? This is a slight dump of ideas of what might be possible. And in the next 3 slides, we will introduce 3 standard eBPF tools to investigate which de-optimization method in Graal's libjvm.so are important. So firstly, the standard frontcount tool in eBPF can instrument any methods that match or are related to deoptimization in libjvm.so. We can easily identify which functions are called and how often. Next up, we can use the standard Flink latency tool to identify histograms of execution latency related to deoptimization in libjvm.so. And obviously, we identified that last frame adjust is one of the most frequently executed deoptimization methods. So here we look at the histogram of its execution latency, and we can see that although it has a lot of executions with reasonable performance, there are some long latency executions that do occur less frequently. We do this, or the tool does this, by instrumenting function, entry, and exit, and timing, the difference between them. Now, next up, we can use Flink Slower, again, a standard tool, to identify the Callstack context. We can selectively instrument libjvm.so, the entry and exit, so that if the latency exceeds a set value, we can selectively print the call stack. So it's possible also to capture the kernel stack as well. So this is particularly useful as it enables us to trace and identify the context why a particular long-lasting operation has occurred. Aspects of the functionality identified in the Flink count, Flink latency, and Flink slower are one part of what we do in our tool. So we've given you some context of what's possible with eBPF. So let's get back to how we can use full stack execution behavior related to microarchitecture. Basically, the eBPF tools enable you to put a problem like deoptimization under a magnifying glass or a microscope. Now, the question now is, how can we relate this microscope view of behavior to full stack execution behavior? Well, we mentioned that when deoptimization occurs, we expect less optimized code to be executed. So this is expected to lead to lower code execution efficiency and or different execution behavior. Now, an important concept is top-down analysis gives us a structured methodology to understand the execution behavior on modern out-of-order processes. And in out-of-order execution, many instructions are concurrently in flight, awaiting resources or results to become available before they can be issued at the front end or retired and completed at the back end. Top-down analysis is a well-accepted way to analyze performance. Intel and ARM have tools and metrics for their own out-of-order processes. Different sets of performance counters are used to relate the fraction of processor cycles that are limited by a specific issue. At the top level, front-end bound represents issue slots to the processor that are underutilized. Bad speculation represents the fraction of slots that are wasted due to incorrectly speculated branches. Back-end bound represents the fraction of slots where micro-operations cannot be delivered due to a lack of resources in the processor back-end. And retiring is a really, really important fraction, as it represents the fraction of slots utilized by useful work. To emphasize, optimizing utilization of the microarchitecture means improving the retiring fraction. If a particular top-down metric is high enough to merit further investigation, then another set of performance counters is used to distinguish, for example, between core bound and memory bound, and so on. We've also highlighted on the right-hand side that the Renaissance benchmarks having the highest front-end bound, back-end bound, bad speculation, and retiring fractions. But this top-down information here is aggregated over the entire execution, and we used Intel tools to generate this. It doesn't give us any insight into the dynamic behavior over time windows, for example, during the warm-up, nor does it tell us how different threads in the application and or from the VM perform. And we would expect compilation threads, garbage collection threads, and application threads to have radically different behaviors. And also, this accumulated behavior cannot tell us the impact of a JVM event like deoptimization. We've shown you some Renaissance behavior and demonstrated different top-down issues across different benchmarks. What about GraalVM? Does it display similar execution behavior? For this, we have taken a selection of Polybench C benchmarks, compiled them to LLVM-IR, and also compiled them to WebAssembly. For each benchmark, we see the top-down behavior of the LLVM, Sulong, and then the WebAssembly, both executed with GraalVM. We can see that the GraalVM execution of LLVM and WebAssembly can have different behavior on the microarchitecture. Although not shown, different performance is evident too. Again, this aggregated or average behavior doesn't tell us how different threads behave. What about dynamic behavior? When we're executing different code or differently compiled versions of the same code, these things will be obfuscated. So this is a motivation for why we need to see dynamic timeline information of top-down behavior and JVM events from libjvm.so. So the full stack concept, the full stack concept with BCC Java, we use eBPF with a Python front end to perform tracing of each thread's time slice on a CPU. We log the changes in performance counter values during a time slice, and we do this by instrumenting the OS scheduler trace point. We're developing a set of Python scripts to visualize and analyze the logged information offline. And this is a short snippet of output for one core. It displays the top-down dynamic behavior on that core. And we can see that the retiring fraction, indicating useful work and effective utilization of the processor microarchitecture, changes over time. Why is this? And how can we find out what causes these changes? Well, BCC Java also instruments JVM events in libjvm.so, and we can try to identify the causes, or at least correlations, between changes in effective utilization by overlaying the start, stop, and durations of instrumented events. This is very much work in process. We have the basic technology working. We're trying to make it easy to select arbitrary events and to improve visualization and analysis that we use to identify performance issues. We're currently using Python scripts to analyze our data, and we're looking into identifying program execution phases by looking at change point analysis. One of our PhD students is using the tool to investigate microarchitectural issues in Maxine VM on ARch64. So the conclusions. Better tooling is needed to make it easy to instrument GraalVM and JVMs using perf and eBPF. For example, better support to identify or instrument jittered code addresses. We've seen that even standard eBPF tools can extract useful information in instrumenting libjvm.so. We've seen that flame graphs can visualize information where time is spent at reasonably low overhead, but we haven't demonstrated how we can visualize difficult performance issues. Okay, so performance issues can be obscured in a flame graph. We've tried to highlight that full stack tracing, performance counters, and selective call stack capture can act like a magnifying glass for identifying performance problems. And I'd like to summarize that the novel aspects of our tool is that we do dynamic thread level behavior that's overlaid with event traces. I've got some questions to kind of throw out for discussion. Does the community have any important performance problems or use cases they can share? For example, information on what GraalVM code or events to trace for a given use case. How might one implement tooling to selectively dump the Graal IR for a compilation unit? And how to identify the performance impact of de-optimizations. Can we identify the impact of executing less optimized code? And I'm particularly interested in recommendations for performance optimization, information on GraalVM internals, tutorial examples, and information sources. And on the final slide I have is some acknowledgements from funding sources. So that's all I've got to say. Are there any questions?
Hey, Andy, so I have a question. So you mentioned BCC Java. Is that like a separate project? I don't know that project.
That's my tool. That's what I've written. So basically, we're using the Python front end to eBPF, the BCC tooling. There are many front ends to eBPF. Okay, so but this is just the one that we're using. Basically, you can write a C-like event-driven program that's then JIT compiled to the eBPF. Yeah, and you can use the Python to handle some of the difficulties or the issues of loading and unloading the instrumentation and getting the information to user land.
That sounds very useful. Is it open source or available?
So we normally open source our work. Obviously, it's still kind of a work in progress, and once we've got publications of things, we open source it, and we have a track record of doing that with our Beehive Lab Git repository. So it's not open source yet, but we plan to in the future.
Thank you. And you mentioned things that might be interesting to the community. For us, I see we have lots of problems with Scala code bases and method dispatch for interfaces. So being able to probe and see like what kind of objects and classes are going through the interface dispatch would be very useful.
So I think that's a very interesting question, because obviously one thing I don't want to get bogged down too much in details now, is really pushed for time, as you can see. But you can also read the arguments of the things that you trace. So if you've got like a particular function argument, you can actually grab hold of that and read it. So that might be very useful for you there to see, to analyze not only just what do timing or measure microarchitectural behavior, but also to actually read the parameter values to methods.
Thank you.
Any other questions for Andy? You should definitely join the Graal Workshop Slack channel, and Andy, you can share your slides there, and especially your questions that you had for the community at the end. We'd like to have a good discussion on that. Thank you, Andy.
Good, thank you very much.